Hello everyone, we are BK Auto Team from Hanoi University of Science and Technology, Vietnam.
Modern ACC systems help maintain vehicle speed and a safe following distance, but traditional controllers, such as PID, often lead to jerky behavior in low-speed urban traffic. In contrast, human drivers rely on perception and experience, allowing them to respond flexibly to small changes in the traffic environment. Motivated by this, we develop a fuzzy logic controller that mimics human reasoning, enabling the system to make softer, more adaptive decisions in complex traffic situations. This approach is particularly well suited to the Vietnamese urban context, where traffic density is high and infrastructure conditions remain challenging.
The system operates by measuring the distance between the host vehicle and the vehicle ahead. The signal processing flow is organized into two control layers. High-level control. Fuzzy logic is employed to evaluate the inter-vehicle distance and the relative velocity, determining how much the vehicle should accelerate or decelerate. Low-level control. Once the desired velocity is determined, a PID controller is used to precisely regulate the throttle and brake so that the vehicle reaches and maintains the target speed. To realize this concept, we employ a simulation-based model to make the reset process safer and more cost-effective. Since no reference vehicle was available, we first designed the 1/10 scale physical model and then used its parameters to build the corresponding simulation model in MATLAB Simulink. After completing the 1/10 scale physical model of a real vehicle, we developed the simulation model based on its parameters. The simulation consists of the following component models: the electric motor, battery, braking system, wheel model, and the longitudinal dynamics of the electric vehicle. To simulate the motion of the two vehicles in a Simulink environment, we used the driving scenario designer integrated in MATLAB to create the test scenarios. Driving scenario designer allows export to Simulink. The scenario reader block reads the object from the base workspace and then reads the actor data from that object. The driving radar data generator block generates radar sensor data from a driving scenario. The vision detection generator block generates detections and measurements from a camera mounted on the ego vehicle. Next, the fuzzy controller model takes the relative distance and relative velocity as input and outputs the desired acceleration. This acceleration is iterated to compute the desired speed, which is then compared with the actual vehicle speed. The difference between these two values represents the error, and this error is used as the input to the PID controller. As they know, fuzzy controllers work with linguistic variables instead of precise numerical values. The inputs are classified into 5 levels: relative distance, very close, close, medium, far, very far, relative speed, large negative, negative, 0, positive, and large positive. Next step, the Memdani inference system employs fuzzy sets. The output is also divided into 5 levels, corresponding to accelerating, maintaining speed, or decelerating the vehicle. The PID controller uses the desired speed from fuzzy logic and actual speed as input and generates motor or brake control signals. The simulation is carried out in the Simulink environment, where the following vehicle starts 0.1 meter behind the leading vehicle. The leading vehicle is placed in a scenario representing realistic Vietnamese rush hour traffic and is scaled appropriately for a 1/10 scale vehicle model used in experiments. The velocity profile is provided as an input to the driving scenario. The driving scenario is implemented on a straight road over a duration of 40 seconds. The following vehicle is equipped with a forward-facing radar sensor mounted at the front. The simulation results show that when the speed of the leading vehicle changes, the speed of the following vehicle adjusts accordingly to maintain a relative distance of approximately 0.50 meters from the vehicle ahead. This demonstrates that the controller operates effectively at low speeds, ensuring stability and responsive behavior in maintaining a set following distance from the leading vehicle. This project has designed an ACC system for electric vehicles operating at low speed ranges using a fuzzy PID controller. The simulation and experiment results demonstrate that Under fuzzy-PID control, the host vehicle can maintain safety relative distance to the preceding vehicle and operating smoothly. The error between the simulation model and the physical model is less than 10%, indicating that the model is suitable for use in the further studies. Future scopes: integration of regenerative braking analysis, studying the 3DOF model and implementing scenarios on curves, consideration of cut-in and cut-out maneuvers,